Sure. Right. So, for those of you that are here for the homework stuff, we will start with that stuff. I'm going to go through some questions. If you are here in year 11 and you have some questions, then feel free to ask those as well. Um, but otherwise, I will start with answering the questions that have been asked, which has started with 1657 in this booklet. Right. I think the first question I know what it is, and it is that density practical thing, which is here. Um, so that's one. That's booklet two. Two and three are the same this week, which is makes life easier. There's year 10 one for later. Okay. So um going through some of these will overlap, I think, across the two booklets. I'm fairly sure. Let me see. Yeah, I think they might end up all being the same. I've got a feeling. But we'll find out in a moment. Okay, so this entire topic, I'm just going to quickly give you a brief overview of what's going on here. Um, this topic is about the fact that it is about something called density. Density is calculated um, by dividing the mass of an object, which is how heavy it is, by the volume of the object, which is how much space it takes up. Density is a measure of how tightly packed particles are, which is just a property of any material. Every material has its own density, basically. Now, the point of this topic is that if I want to find the mass of an object, it's really easy. I can use a scale, just put it on top, and it'll give me that. But for volume, the problem with objects that look like this is that I can't like use a ruler and measure things. Like if I gave you a cube and I said, find the volume, well, you could measure this side, and this side, and time them together. You can use a ruler basically to find the volume of an object that looks like this. It's because these objects are called regular objects, whereas objects that have like holes in and aren't nice shapes, like rocks, are irregular objects. And you can't, with an irregular object, calculate its volume just using a ruler like you can with an object like that. You can measure something and time them together. With these things, because they have an irregular shape, you cannot find the volume just using a ruler. There's another method to do it, which I think is identified here. Okay, so let me again give you a bit of background before I go into this. If I told you that this is a bathtub and you filled it with water to the very top and then you got inside it, what would happen? Well, the water would overflow and come out. But how much water would come out? Well, the amount of water that would come out is exactly the same volume as your volume. In other words, the amount of space that you take up, because that's why it left, is because you're taking up that amount of space now, which is essentially the point of this. If you are able to do something like this, you could basically find out the volume of anything because it is easy to find the volume of liquids using a measuring cylinder. And what I've done here is essentially turned the volume of this person into a liquid, and then I can measure the volume using a measuring cylinder. We basically do the same thing by using this as our bathtub, so to speak. What we do is we fill a displacement can with water. Up to the spout. This thing is a spout. Okay, so you fill it with water up to here. You then drop in your object. So you put the limestone in. So you're trying to find the volume of this object. Okay, when you drop the limestone in, this water level will rise, and as soon as it starts to rise, it'll start coming down this spout over here. And what you do is you collect the water that comes out here in a beaker first if you want, and then put it in the measuring cylinder, but you may as well just put the measuring, oh, let's put the beaker there. So collect it in a beaker. Okay. So you collect the water that comes out in a beaker. Now remember, the amount of water that comes out must be the same as the volume of the limestone that you put in because that's taking up that much space. So because they've mentioned beaker here, I'm going to do it all. I'm going to say collect it in a beaker first. Then pour the water from the beaker to a measuring cylinder. And then remember the point we're trying to do here is determine the volume of the limestone. And because we've now got some water in a measuring cylinder, it will tell us the volume of that water. And the volume of the water is the same as the volume of the limestone. Okay. 1657, 1B, that was 1B. I think these are all the same. So I'll say I think I'll just be able to go through this whole booklet. I'm pretty sure that all of them is the same this time. But tell me if not. I shouldn't need to do this question, but it says calculate the density, which is this number divided by this number, which I think gives you 2.5, I think. Yeah, I think it's 2.5. Um, okay, and then density can be measured in grams per centimeters cubed. What is another unit for density? Well, what else can we measure grams in? We can measure grams in kilograms, not kilograms cubed. That doesn't make sense. Which means that is actually the answer because volume can be measured in centimeters cubed or meters cubed, and then the units change in correspondence to that. Um, this student has a sample of an unknown type of rock. Density is 2.4. Draw the bar. So 2.4 is like there somewhere. So you'll have a bar that goes like that, something like that. The data suggests that the unknown type of rock is, well, the idea of this question is that the density of this rock and this rock is exactly the same, which suggests that those two are the same rock, obsidian. Hmm. You cannot be certain though. Why? Because the different rocks might have the same density. Just because you've got the same number here doesn't mean exactly the same rock. So, um, different rocks might have the same density. It's just a measure. It doesn't mean that it's unique. It can be that different rocks have the same density. Okay. Pumice is a type of rock that has holes in it. Which diagram shows the arrangement of particles in air? Surely it's this one. Okay, that's basically a solid. That's, I guess, a liquid. That isn't anything. Um, that's going to be a gas. The holes containing air cause the density to be something than the density of other types of rock. Um, Density is a measure of how tightly packed the particles are. If there's air spaces in the middle, then they're not as tightly packed together, which means the density is lower, right? I think that'll be less than because of these holes containing air. I think you can do that. Why gases are easy to compress, I'll just say this in words. Because the particles in a gas are very far apart, they can be pushed closer together. And that's what we mean by compressing. The reason I can move my hands closer right now is because the air has got loads of gaps between the particles, and I can bring those particles closer together so I can move my hands. With a solid, I can't do that because the particles are already really close together. Okay, I don't know what question I'm doing anymore. One, six, five, seven. I started doing two, didn't I? Let me do six. Um, Six is here, so there are waves and stuff involved in here. What do all waves transfer? All waves transfer energy, so that is that. Different types of electromagnetic waves have different wavelengths, and because they have a different wavelength, they have a different frequency. The thing that's the same about electromagnetic waves is they all travel at the same speed, but their wavelengths, the different radio waves, for example, are really far apart like that. Gamma are really close together like that. Give the names of this. You should learn this electromagnetic spectrum as best you can. Let's see if I've got any questions here. Um, the thing on the computer didn't really work. So what did you do? I don't understand what that means. Um, what do you mean by the thing on the computer didn't really work? I believe this is being recorded. Yes. Um, yeah, what do you mean by the thing on the computer didn't really work? Um, the thing on the computer. Which question are you asking me about? Are you asking me about a question? What did you answer? Ping on the computer. Anyway, I want to carry on until you tell me what question number you're asking me about. These names, so you want to try and remember this in order. Radio, microwave, infrared. Visible light is the one in the middle. And then it goes ultraviolet, X-ray, and gamma at the end. You should learn that. Um, is it different to booklet three? Okay, fine. I'll get to booklet three in a second. And then two and three are the same, I'm pretty sure. So let me just check. Yes, fine. I'll get to that. Let me just get through one first, and then I'll move over. Um, four. I'll get to four. That's not in this booklet. I'll come to that in a minute because you're asking me about booklet two when you say question four, I think. So I'll come to that after I've done this. So, six, five, and seven. One, six, five, and seven. So one, five, six, and seven. Okay. Um, so six. The uses of these microwaves are used in satellite communication. Ultraviolet will be used in energy efficient lamp. X-rays obviously for bones. All right, and then five, and then I'll move on. I'll see if anybody has any more questions on booklet one, but I don't think there are. Five, again, uses. It's tricky, isn't it? Visible light, I guess. Photography. Um, radio waves will be for TV broadcasts, I'm pretty sure. And then microwaves probably for mobile phones because it's a satellite communication. Um, I'm going to go with that. And that is question five done. So I think that's, is there anything else for booklet one that I need to do? Um, two, I'm not going to do that one. I've explained that one. Let me have a look at this one. Um, shouldn't really need to do that. The motion of the ball bearings, how is it similar to gas particles? It's because they're flying around and are very far apart, just like they are in a gas. The faster the motor runs, the faster the ball bearings move, increasing the speed is likely the temperature of gas. Well, predict what happens to the speed of the gas particles when the temperature is increased. Well, they'll travel faster. The particles get hotter, they move faster, basically. Um, booklet three, two, I don't understand what's happening here. Right. So I'm going to move on. I think that's all of booklet one, I think, done. At least any questions from booklet one that I can see. And then booklet two and booklet three are the same. So now I can just move on to that and answer any questions specific to this. Starting with what we are asked, which was 4A, 4B. Let's have a look. Okay. State one example of the use of each type of radiation for communication. I think for infrared, you want to put remote controls. Most TV remote controls use infrared radiation, and microwaves are used in communicating with satellites. That's what that is. Some of the properties, right? Remember, these are electromagnetic waves. So their properties, first property that I would say is the same is that they travel at the same speed because all electromagnetic waves travel at the same speed, but also they're waves, aren't they? So what do we know about waves? All waves transfer energy. Or you can say that they reflect or that they refract. Things that all waves do are properties of both of these things as well. Um, and then did anybody ask about question five? No, good. 6B, 6D, 7D. I'm just doing it in order that it was asked. Okay. The name given to reflective sound waves, you should really know that. If you shout out really loudly and then you hear your voice back, it's your sound wave being reflected, which is also known as an echo. Um, D. Describe a longitudinal wave. That is a definition for a longitudinal wave, which you really should have in some previous notes, which is in a longitudinal wave, the vibrations are parallel to the direction of travel. of the wave. Um, that's 6D, and then you also asked for 7D. I'll go back and I'll just go through anything that I missed. The uses of these, I think we've done this, right? So the same question. So microwave, satellite communication, ultraviolet, energy efficient lamps, I think X-rays for bones, right? That's all of that done. Um, three, 1B. Have I done that? I think I've done 1B. So I've done that question, which was from earlier. You can watch it back 'cause it was the same booklet. 3F. Um, how are they used in communications? That's hard. Um, right. Microwaves are used in communications because they communicate with satellites. Um, and I'd mention one more thing because it's 4 marks here. The reason they can communicate with satellites really well is because microwaves can travel through the Earth's atmosphere. Because the satellites are on the other side of that. And then I think with this one, how are they used in communications? I think I remember the mark scheme for this. I've got it open, but the idea of this is, well, how how is light used for seeing things? It's because it can travel into your eyes and bounce off objects. That helps you see. Like, for example, a traffic light, you can see it because the light can travel um, in straight lines. I don't know if this is the answer, but I'm going to go with it. Um, and it reflects off surfaces. That's why we can see things. I want to put e.g. A traffic light. That is a light that is communicating with you. There is another answer for that, which is fiber optic cables. You can answer that question. Let me see what else is going on. Um, so when you say they're not the same, what do you mean? This question here is not the same question that you've got on yours. Is that what you're saying? Anyway, I'll keep going until I get any more. 316. I've done that. 60, 70. I've done that. Yeah. Okay. Did 3F just now. Um, 3 and 4 in booklet 3. Did I do that? Yes. Done all of 3. Well, not all of 3, but I'll let you try that one. Um, I'll let you. Oh, God. Yeah, I mean, during one X-ray, a person receives a dose of this MSV. Why is this unlikely to harm it? Because you're told that 100, which is much bigger than that number, has a slightly increased risk of cancer. Now, this is way smaller than 100. In fact, it's 100 times smaller than, no, not even 100 times smaller than 100. It is a million times smaller. So this is a lot smaller than the amount that only gives you a slight increase, so it's very unlikely to harm you. Um, why does the doctor stand behind a screen? Because they don't want to be exposed to the radiation from the X-ray. Um, gamma, I think, is used for sterilizing medical equipment out of those. And the reason these are harmful is because they are ionizing. Ionizing means that they can sort of hit your cells and cause them to be damaged. Well, that's what it really means. Um, and then I did all of 4 anyway. And then 4 on booklet 2. I did that, didn't I? Yeah. Okay. 4 on 2. Yeah, okay. Did that. 2 is not the same. I still don't understand what you mean by this. Um, this is, oh, this one. It's not, it's okay. Question 2. I think you were saying, I thought you were saying question 1. Sorry. 2. Okay. Question 2. I'm just going to again summarize this quickly because you should have a reasonable understanding of this. Um, in a solid, you have to basically describe solid, liquids, and gases using their arrangement, the movement, and energy of their particles. Words you want to use are things like fixed, regular arrangement for a solid. You want to say that the particles vibrate in one position. You want to say they have very little energy. That would be enough for solid. For liquid, you want to say that these particles are in an irregular arrangement. You want to say that they can move past each other. And you want to say they've got more energy than the particles in a solid. And with a gas, you want to say that they fly around in random directions. Okay, you want to mention that they have the most energy of the three. And I think that's enough to get all the 6 marks, really, when it comes to that stuff. Um, all right, where are the questions? 2C on, I don't know what 2C on 2 means, because that's just question 2, unless I missed something. Have I got the wrong thing going on here? No, I've got the right booklet. Um, so this is the booklet I'm currently doing. This is the booklet 2 that you should have been given, and 3. 2 and 3 were the same. I don't know what 2C means because the question is just number 2. 5A, I think I've done, haven't I? Oh no, 5 part 1. Is that five? That is 5 part 1, isn't it? How microwaves heat up food. You need to explain that the microwaves are absorbed by the water in the food. That's how microwaves work. The waves that come out of the sides get absorbed by water. And that water gets hot. And then when the water gets hot, the heat is then passed on to the surrounding food. That's why they're not very good, technically. Okay. 1B and G. Let me see what happened with 1B. I think I answered 1B already. And there isn't a 1G, unless I'm missing something and I've got the booklets wrong. There isn't a 1G. Um, unless you're talking about, yeah. Are we talking about this on booklet 1? That's what it'd be if it's, we talking about booklet 1. You don't know who it is that's asking the question, so I can't really tell you. But anyway, I've done booklet 1. Any other questions? I said to my GC in 2020, I'm year 9. Will I get an equation sheet? I think currently, if you're in year 9 and below, I believe as it stands, you're not getting the complete equation sheet in physics. You get like half of them and you have to learn the other half. But I think that's going to change. So for now, I would just, to be safe, just keep an eye on equations, try to remember them a little bit. But I think you're going to get all of the equations as everybody else has for the past few years. The intention was to change it back, but I think that's not happening. Um, Anybody got any other question on homework then? 3C, again, when you say that, is that booklet 2? If you could just specify the booklet, because people keep saying numbers and letters, but there are more than one booklet here. 3C, I assume that's this one, which I have answered, I think. Yeah. Um, why does the doctor stand behind a screen when you're taking an X-ray? Is because so that they're not exposed to the radiation of the X-ray. Um, that's the idea. The screen blocks the X-ray. You can say it that way if you want. The screen blocks the X-ray from reaching them. Um, 7C, I'm not going to answer, I'm afraid, because I have actually already technically done it. But also, you should know. You should be able to figure this out. 7C. Anything else? Um, Last year, year 11s is this year, year 10s are getting because they missed learning. Yes, I know. So as I said, the intention was that after this, after after next year, year 10s, um, they were going to go back to normal before COVID, which was you had to learn about half the physics equations and not the other half. That was the intention. I think that is still currently the situation, but I think it's going to be changed, which is that you will continue to get all of the equations, even if you're in year 9 now. But again, don't think of that as too big an advantage. It doesn't really make a difference. It means you have to learn a little bit less, but the equation sheet is still not that helpful, believe it or not. 6C booklet 2. Again, I think I've finally answered this. Oh no, I haven't. Right, I'll tell you the equation you need to answer the question, and then you can figure it out yourself. Wave speed equals frequency multiplied by wavelength. That's what you need. And just be careful, the frequency, because it's in kilohertz, you have to make it hertz by timesing it by 1,000. So that's the number you want to use for frequency. The wavelength is in meters, so that's fine. So now you should know what to do. 1I from anonymous attendee. Can you clarify which booklet number you are after? And also who you are, because I would prefer to know who that is. Any other questions? Again, who is asking those questions? Booklet 2-1I, to clarify who it is. The sound hasn't gone. I was waiting for you to confirm who you are. Because if you don't, I won't answer the question. Anybody else got any other questions? Okay, right. Given that there are no other questions from non-anonymous attendees, I will stop now and then I will be back in about 15 minutes for anybody in year 10 or year 11 that wants to do that. Aya, yes. What would you like? 1I, are you asking this question? 1B, I think I've done this. Um, Yeah, I've already answered that question. You'll have to go back and watch back because I did that in the previous booklet, which was the whole process of doing density or finding the volume using your Eureka can. Okay, fine, right. I think that's it. In fact, what I can do is I can leave that here for you to look at because I think I have the answer here. Is there? That is broadly it. Somebody else was asking 1I. I don't know who was asking it. 1I from booklet 2. Anyway, there is the answer. Sorry. There is the answer to that. I'll leave that there and then I will return shortly to assist with anybody that might have any other questions from GCSE stuff. Hello. Right. For those of you in year 10 and above, we did some electricity related questions. And so what I'm going to do is I will just go through this booklet because I think I'll help others that are here as well. Um, in terms of doing a bit of recap of electricity stuff. Now, most of you have done these questions before because I think we repeated a booklet, but um, let's go through this. If you have specific questions, feel free to ask, but I'll just go through most of it, I think. Um, you need to make sure you know the circuit symbols because they'll be quite easy marks. 4B, I shall get to. Um, but a light-dependent resistor looks a bit like this. Ooh, 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 and then a couple of arrows going into there. That is a light-dependent resistor. Um, a student investigates the relationship between current and potential difference. How should they connect the ammeter and a voltmeter? If you have a circuit, an ammeter needs to go in line with the rest of the components. And then if you are measuring the potential difference or voltage, then you put a voltmeter around the component like that. Now, by around the component, we say in parallel. And when it's in line with everything, we say it's in series, which is why an ammeter needs to be in series and the voltmeter needs to be in parallel. And that would be that. Um, um, And then the diagram below shows a sketch graph of the students' results. The LDR was in constant bright light. They concluded that the current is inversely proportional. No. Inversely proportional suggests that, well, it would be a curve with a negative gradient, and inversely proportional would look like this, basically. So what this shows is direct proportion. And also, I think the other mark you meant to say um, that it's a straight line that goes through the origin. That is what direct proportional means. It means it's a straight line that goes through the origin. Um, the GCSE physics exam is after the half term, both of them. The student repeating the investing with the LDR in constant dark conditions. Right, with a let me figure out how you do part D. Sketch on a diagram of the graph for the LDR in constant dark conditions. I don't think it's much different, really. It's just the point of this is if it's constantly dark, um, so for an LDR, you're supposed to know that when it's bright, the resistance goes down, and when it's dark, the resistance is high. How does that affect this graph? It doesn't really affect it, other than you still have a straight line, um, except this time it just needs to be like that way because the resistance is higher, like I said here, the current will be lower than it was before, basically. So because the resistance is higher, you get a lower current for every same potential difference. 4B and all the at the end. Right, what else do I'll skip to that, given that people ask you. This is voltage is current times resistance. And then I guess you have to do some resistance. So the resistance is voltage over current. Just be careful that they give you current in milliamps, which means it is actually 0.0125 amps, and that's the value you have to use because there are 1,000 milliamps in an amp. So you have to convert it before you use the numbers. Let me skip to 4 because people have asked that, and then I'll see what else is going on in 4. 4. Um, okay. 4 heating elements have the main electricity supply. When all 4 heating elements are on, the hob draws a current of 26 amps. Calculate the resistance of one heating element when it is switched on at full power. Ah, Two significant figures. So the current is going to get shared between these components. So these 26 amps, let me get a calculator ready. So in this kind of circuit, the current gets shared. So I think we will do 26 divided by 4. So each of these is getting a current of 6.5 amps, but because it's like a parallel circuit, um, so in a parallel circuit, the current gets shared, but each branch gets the maximum voltage. So the resistance, I'm hoping, is 230 divided by 6.5, which is 35.38, which are two significant figures, is 35. Okay, and then the the table gives the maximum current that can safely pass through the copper wires of different area. Okay, so remember we've got a current here of 26. Um, right, this is maximum current that can safely pass through copper wires. Right, so if you've got a copper wire with this area, then the maximum current is that. As it gets wider, you can get more current through it. The power sockets in a home are wired using cable containing 2.5, so these ones. Most electrical appliances are connected to the mains electricity supply. It would not be safe to connect the electric cooker because we know that the current from the electric cooker is 26 amps. Now, the wires that we've got can take a maximum of 20 amps, and that's basically the answer, isn't it? So the maximum current, which is 26 amps, is more, um, or the current of 26 amps is more than the maximum for a 2.5 millimeter squared wire, which means that you might have too much current going through it, which would lead to the wire melting or overheating, something like that. If you've got too much current going through it, the wire can melt. That's why there is a maximum limit for it. Is there anything else? If current was 1 amp, then it would be 1 volt. Ooh, I'm not sure why you say that. For which question is that mentioning? Yeah, I don't quite make. I don't know what that's relating to. Oh, you're talking about the graph. Are we back to the graph from a while ago? I don't know. Just clarify what you mean by that question, and I'll try and answer it. Um, for B, I've done. Alternate current goes in both directions. Direct current only goes in one direction. That's the difference between the two. And then I'll also just skip over to the 13 at the end, because that was the only other question that's specifically been asked. Okay, right. Okay. Student investigate resistors connected in series in an electrical circuit. The student has a 3-volt battery, a 22 ohm resistor. They don't know the voltage. The circuit is connected incorrectly. Well, that's because, well, the first incorrect mistake is the voltmeter should be over here, right? If you're measuring the voltage of that component. They fix it. Weird. The voltage is 2.1 volts. So over here, we get 2.1 volts. Okay. Um, State the value of voltage across the other one. Well, in a series circuit, your voltage gets shared between the two components. So 3 volts, 2.1 of it's gone there, which means 0.9 must be going over there. That must be the voltage there. They're going to now ask you what X is, I suspect. Oh no. The current in resistor X is 0.041. Okay, so here the current is 0.041 amps. Show that the resistance must be about 50 ohms using that equation. Let me just multiply these two together. Sorry, not multiply them. But resistance is voltage divided by current. So if you take your voltage, which is 2.1, divided by the current, which is 0.041, I suspect you get about 50. And you do. That's it. So, the direct proportion question, let me answer that question. No, it doesn't mean that when the current is one, direct proportion doesn't mean that when the current is one, the voltage is one. It means that if the current, let's say the potential difference is one, and that could be higher, it could be two, depending on how steep the graph is. But what it means, what direct proportion means, is that if I now double the potential difference, I would double the current. That's what directly proportional means, is that they're both increased by the same amount. That doesn't mean that it's by one every time. It can mean that the increase is the same. So if I now did four, it would be double again, so eight. You see what I mean? Right. So that's what proportional means. It's like in maths when you can have an equation that's like y equals 2x, or it could be 3x, or it could be 4x. It just means that if you double this, you end up doubling this. That's what it kind of means. It doesn't have to mean one and one. Okay, back to that. Right, calculate the power when they're right. So obviously this requires you to normally have an equation sheet, which you will have obviously in your exams. But the formula you would look for on the equation sheet needs to have the word power in it. It needs to have the word potential difference, because potential difference is voltage. And it'll need to have current. And you will find an equation that says something like power equals current multiplied by potential difference. And once you found that equation, you then use the equation. The current is 0.041. The potential difference or voltage is 2.1. If you multiply those together, you should get power, which is 0.0861. Hopefully that's the answer. Yes. Um, and then calculate the overall resistance of the 22 ohm resistor and resistor X. Well, didn't we get told? Okay. Okay. We earlier worked out that the resistance of resistor X is about 50. And we know that the resistance of the other one is 22. So I think it's just those two added together. It is. It is literally that. So the total resistance in a series circuit is the sum of the resistances that you have in the circuit. So in this case, it's 50 and 22. So 72 would be the answer. And then, this is nice and easy. Calculate the energy using this equation. It tells you the current, I is current, so 0.041. It tells you the voltage, which is 3, and it tells you the time to use, but time in physics will always be in seconds. So you want to change the minutes to seconds and put that number in there, and that should be the answer. Um, have I missed a question? I haven't. Oh, the mark scheme doesn't have that answer in it. Anyway, that is the answer. Um, I think that's it, isn't it? Okay. Anything else exciting in here? Just for your any electricity topic that you do, you are meant to recognize that this is the graph for a bulb. And you do need to be able to explain this graph, which I won't do for now, but you do need to be able to explain why it looks like that. And then the only other graph, IV graph, is one for a diode, which looks a bit like this. It's because a diode only allows current to flow in one direction, so it doesn't have a section down here. That is effectively the opposite direction. Um, And there's something else I was going to say about those. Oh yeah, there is a whole required practical about how you get a graph like this, which is a separate thing, but you need to be able to explain if you just were given a light bulb, how would you create a graph that looks like this? And there's a whole practical experiment regarding how you go about doing that. Is there anything else to do? This is just knowledge that you're supposed to have about the UK. In the UK, the voltage or the potential difference is 230 volts and the frequency is 50. Sometimes that question does just appear to see if you recall it. Hmm. Right. Any other questions about anything? I'm just wondering whether we need to do too much more. Um, I am going to do one more little thing about electricity, which I think is important to understand, because you might not have done this in the lesson that you had. Okay. Just a little concept that's really important in electricity to know about, which is that if, for example, this is a 12 volt battery, and these two components, let's say they're exactly the same. If they are exactly the same, then this voltage gets shared equally between them. So that would get 6 volts and this would get 6 volts. But let's talk about what I mean by they're both identical. If they're identical, it means that their resistance is the same. So let's say this is a, how can I get these numbers to work well? Yes, let's say this is a 3 ohm resistor and this is a 3 ohm resistor. Because they have the same resistances, they share the voltage equally. But if this was a 4 ohm resistor and this is only a 2 ohm resistor, then it changes. They don't split it equally. Essentially, the voltage is shared in proportion to the total resistance of the circuit. So what I mean by that is, because this is a 4 ohm resistor out of a total of 6, it gets 4/6 of the voltage. 4/6 of 12 is 8 volts. And this one gets 2 out of 6 of 12, which is 4. And so that is how the voltage is split between those two. Essentially, if you've got twice as much resistance, you get twice as much as the voltage. Um, and if I increase that even further and said, how could I make this work even better? Well, I suppose if this was an 11 ohm resistor, and this was a 1 ohm resistor, then this would get 11 twelfths of the total voltage, which obviously is 11. So this would get 11 volts, and this would get the other 1 volt. So my point of this is that you can change how much voltage goes in these directions by changing the resistances of the component. So if I want this to have more of the voltage, I want it to have a bigger resistance. So if I now make that, I don't know, 12, it's now a slightly bigger fraction. It's now 12/13 of 12. So it's going to get a bit more than 11. If I wanted this to have none, then I could change that to 0. If I change that to 0, then now this doesn't get any of the voltage. It gets 0 volts, and this gets all 12 volts. You see what I mean? 'Cause it's now 12 twelfths of 12. And the reason that is important to understand is because it's basically how components like LDRs and thermistors actually work, because they have resistances that are variable. And so what an LDR and a thermistor can do is essentially pull more of the voltage in one direction. And then you could, for example, so if I've got a thermistor which looks a bit like this, for example, um, I can pull more of the voltage this way and then maybe connect a light bulb here. So I can, in some instances, have a lot of voltage here and light this up, or I can have very little voltage here and send more of it that way, so this bulb turns off. It is a little bit of a complicated concept, but it is how most complicated electricity GCSE questions work. They are testing whether you understand that by this resistance going up and down, it can take more or less of the voltage from the battery. This will stay fixed. It doesn't matter. As long as this is fixed, it doesn't really matter what it is, because as long as this gets really, really high, it can take more of that 12 volts. If it gets really, really low, it can take less of it. And that's how we can, for example, turn something on when it gets really cold or turn on a light when it gets dark. It's because these components have resistances that can change. And there's one particular question that I'm not going to find now that used that concept. Um, to see if I can find it in a moment. Okay, I'm going to go through one more question on this, and I think that'll be it today at least. And then I'll say if you're in year 11, obviously you have other exams this week anyway, but I'll be available tomorrow and stuff. And the English language tomorrow, isn't it? Um, Here is a question that says that there is a vending machine here, and it asks you, as I said earlier, the frequency of the potential difference of the UK electricity supply, 50 hertz, 230 volts. And then it says a question. As I say, most of these questions you should not be afraid of because you get a formula sheet which will tell you the equation at least that you need, and then you have to trust your maths to be able to do stuff like this. So, when you see these questions, obviously the scenario could be anything, but you're looking for words: resistance, current, power. Okay. And you look for an equation that has those three words in it. And I'm pretty sure there is an equation that says something like P equals I squared R, which is power equals current squared times resistance. So the power is 340 milliwatts, which is 0.34 watts. You've got to change that. The current is 0.75 times resistance. We're asked to work out what resistance is. So it's 0.34 divided by 0.75 squared, which turns out to be about that. Okay. Okay, so I'm just going to explain this without doing the actual question. I'm going to explain what's going on here. Questions? No. Okay, right. Um, I'm going to change that situation a little bit. Okay. I'm going to change this V to something else. I'm going to change it to an M. Think of this as a motor. This is a fridge, basically. It's a vending machine with a fridge. Okay. Think of this as a motor that is, when it turns on, it cools the fridge down. Okay. So how does this work? We have a circuit here with a fixed resistor and a thermistor. The thermistor is that circuit symbol, something like that. So how does this happen? Well, what you need to know about thermistors is that when the temperature is high, the resistance is low, and when the temperature is low, the resistance goes up. Okay, so let's pretend that it is very cold already. if they're very cold already, then this thermistor detects a cold temperature. We do not need this motor to be on at the moment because it's a fridge and it's already cold. So you wouldn't want to waste electricity or whatever by turning that motor on. And so when it's really, oh, I've got this wrong way around. Sorry, that's not there. Oh, change this. Okay, let me redo the circuit. Um, okay, so this is the circuit. This is where that motor is that I mentioned that will turn on when it gets too cold. So let's pretend right now, when it gets too hot, sorry. So let's pretend now it is very, very cold in this fridge. Already we don't need this to be on. So if the temperature, this thermostat detects a low temperature, um, its resistance will go up. Okay, so that's what happens when it detects a low temperature. So let's pretend this resistance, remember it's variable, it can go up or down, gets really high. So let's make it, just for the sake of argument, 10,000 ohms. Okay, so it's gone up because it's detecting a very low temperature. Now, remember what I said earlier about these circuits? The voltage from the battery gets split depending on the resistances of the components. So right now, if we just do the maths here, in total, the resistance is 10,400. I just made it up that way. And this component is 10,000 of it, which means it's going to get a lot of this 12 volts. Let's work out exactly how much. Going to get 11.5 volts of the 12. Okay, so this is going to get 11.5 volts, and this is only going to get half a volt. Okay, in other words, that's a very, very low voltage, which means this motor isn't going to turn on if maybe a tiny bit, but not really. This doesn't do anything. It just, all it's doing now is it's pulling the voltage that way away from the motor so that the motor doesn't turn on. We don't want it to turn on because, as I said, this is a scenario where the temperature is already low. When it's already low, we don't need this to turn on to cool down this fridge. And so by having its resistance go up to a really high level, it effectively steals a lot of the voltage away from this component. Now let's pretend that it starts to get hot. Okay, so whatever, it's a hot day and it starts to get hot. What happens to a thermistor when it starts to get hot? Its resistance starts to fall. Let's just, for the sake of exaggeration, say that its resistance now falls to just 1 ohm. Okay, so it's gone really low because it's detecting a very high temperature. That's what it does. Um, Now what's going to happen? Well, now the total resistance here is 401. How much is this going to get? It's going to get 1 out of 401 of the 12 volts, which is obviously a tiny number. 0.03. And the other one is going to get most of it. So that's going to get 12 minus that, which is 11.97, basically all of it. And what's that going to do? By sending more of the voltage this way, you turn this motor on, which is exactly what you want to do when there is a high temperature in that fridge. And so that turns on the motor, which starts to cool it down. And so what this thermistor is doing is basically redirecting the voltage from one place to another, depending on the temperature. And I think sometimes people misunderstand precisely what the point of that is. Um, you are basically finding the percentage of the resistance in each, yes, but not, I'm just doing it as a fraction. You don't need to find percent, but you can do it as a percentage if you want. But I'm just saying, yes, the fraction of the 12. So yes. So essentially, yes. When that was 1 and this was 4, remember this 400 doesn't change. So in this scenario, this thermistor is pulling 1 out of 401 of the 12. Whereas in the previous scenario, so it's basically taking most of that 12 volts there, and less of it is going to here. So we're redirecting. We're basically able to turn this motor on or off based on what this thermistor is doing. And when the temperature gets really cold, then now the resistance of this will increase. So let's say it increases to 1,000. Okay, so now this thermistor will get 1,000 out of 1,400 of the 12. And often you get these questions where they ask you, what is the voltage across this component or something like that? And basically you can do this. There is another way to do it, but I think it's better to understand it like this. You can work out the total current in the circuit and do a slightly longer calculation. But that means now this is getting 8.5 volts and the other one's only getting whatever the difference is, 2.5, 3.5. So before this was getting most of it, now it's getting a lot less of it. And the reason it's getting a lot less of it is because the temperature has fallen and we don't need this motor to be on as much. And therefore we are able to sort of redirect voltage. Yes, so I'll just go through these a couple of questions that somebody has sent to me, and then I will be done for today. Okay, I probably won't read. I'll just explain them as I go because I've got them on here. Okay, so this is to do with waves. Suddenly, just switching a physics topic out of nowhere. But let me do the illustration here. Right, this is some water. This is shallow water, and this is deep water. Then we have some waves coming towards this, but then when they hit here, they seem to. I've drawn that really badly, but they seem to bend when they hit this. And the question is essentially, this is called refraction when a wave bends. Why does it happen? Refraction only happens because of a change in speed of waves. Okay, so what's happened here is that when this wave has gone from deep to shallow water, it has changed speed. In shallow water, it actually travels more slowly, and in deep water, it travels faster. Now, because one side of this, if you just imagine, let me just do this like this. So if you imagine this wave coming towards the boundary, then you see this part of the wave there. That hits the boundary first, which means this section of the wave changes speed now because it's hitting shallow water, so it starts to slow down now, whereas this one doesn't hit that, so it's going faster, right? So this top part of the wave, imagine it's going faster than the bottom part of the wave. That means that kind of pulls out ahead, causing the wave to effectively bend as it enters the shallow water. So in order to answer that question in full, you want to say that this refraction happens because the wave changes speed when it goes from the deep to the shallow water, and because one side of the wave hits the shallow water first, it slows down first before the other side, and that causes the whole wave to change direction. It is the equivalent of, I mean, this is a weird example. I'm going to explain this. Right. Imagine that is a car that is very quickly traveling from a road and is about to hit like some mud. There is the mud, okay? And it's going to hit it at an angle. Now, if it hits at an angle, that wheel there hits the mud first, which means it starts slowing down, whereas the rest of it doesn't hit the mud, which means that these wheels on this side are traveling faster than this wheel on this side, basically causing this whole vehicle to bend a little bit. And that is what refraction is. It is due to the different speed of it. And that kind of answers the next question, because the next question said that if you have this situation, deep water here and shallow water over here, and these waves are coming here, why don't they change direction? It is because they're not hitting it at an angle. They are parallel to the boundary, which means remember the previous thing happened because one side of it slowed down first. Here, they all slow down at the same time, so their wavelength decreases. Um, the wavelength decreases, but the direction doesn't change because they are hitting it parallel. It's like the same equivalent of the car coming straight at this mud. It wouldn't change direction because they're kind of everything's happening hitting at the same time. It's the angle that makes the difference. And then the rest of this was relatively straightforward. I'll I'll do the radioactivity one you sent separately, so like tomorrow or the day after, because it's because I need to draw it. But the other one is a student wrote coal traps energy from the sun. What does this mean? Well, it's coal is a fossil fuel. It is the remains of dead plants and animals. Plants take in energy from the sun for photosynthesis, and then they die and reform as coal. That's what it means by coal traps energy from the sun. Do you see what I mean? That's the idea. It's a bit of a weird one, but it's kind of the idea is fossil fuels do ultimately trap energy from the sun. It's just they do it via plants. So plants take it in, plants die, and then they reform as fossil fuels. Energy is released from coal by burning it, or combustion is a more complicated answer. So yeah, I'll do the radioactivity question with you tomorrow if that's okay. Right. I think that's all I'm going to do for today. Again, those of you in year 11, what day is it tomorrow? Thursday. I will be around at 7 p.m. should you have any questions. And then after that, all throughout the half term and during half term, I might do some extra stuff should you want to join because you'll be available during the day.